Section 4.7 is called value of the induced voltage. So what we're going to do is we're going to take all that information and sort of theoretical stuff that we went through in the first 6 sections, and we're going to incorporate our first equation from chapter 4, 4.1, and we're going to look at some particulars about DC generators and go through and make some calculations. And you know, instead of this just being some exercise where we plug numbers into an equation, since we know what's going on internal to the generator, it should help make sense of all this for us. Okay, here we go. So what we're looking at here is, you know, just a representation of a DC generator. This was back when this is a schematic, of course, and this was, you know, talking about, you know, the 12 coils, and, you know, we were working through that. But I'll just bring that up here, and I want to point out our equation. In the there's a voltage developed on a DC generator armature, and it is given by this equation 4.1, and E, of course, for voltage. It's the voltage between the brushes. The Z number is the total number of conductors that reside on the armature. The N is the speed of rotation, and that's in RPMs. And this is the flux per pole, and that would be in Webers, okay? So it's the flux per pole, not flux density, which is Tesla, but flux per pole, which is in Webers, all right? And then the 60 is there, and a lot of times you see this because you're going back and forth between values that are, you know, in like, you know, per minute, per second, you know, that sort of thing. But the 60 is just a number because the speed's given in RPMs and so forth and so on. Again, we're not deriving this, and that's not critical, but, you know, I just point that out to you. Now, as you go through and you work with this equation, the thing that I will point out is the hardest part of it is just determining what the Z number. Everything else is straightforward and all. And then the other thing that, you know, he tells us is that this voltage, or this formula for voltage, is only holds true if the brushes are in their neutral position, okay? And so we assume that that's happening. If the brushes were shifted off neutral, and we're going to see how that can happen in a little bit, then that throws this equation off. So he says, let's say that we have a 6-pole. Now this is new because up to this point, you know, we've only had, you know, 2-pole motors, but I mean generators. But just imagine that instead of just having the 2 poles, we had 4 additional poles. Now adds a lot of complication to it, you know, and we try to understand it and all that, you know, it's harder to see. So, you know, that's why up to this point we've looked at, you know, 2-pole generators, but a 6-pole generator would just have more magnetic flux available, right? So, and that's more realistic. And it's turning at 600 RPMs, and it has 90 slots. Each coil has 4 turns, and I'll tell you a little bit about that in just a second. So each coil has 4 turns, and the flux per pole is 0.04 Webers. Now, I'm going to focus initially on this, and he says calculate the value of the induced voltage. So let me just bring something up first. Okay, so if we were looking at a motor coil, you know, we think of it as got one side, and then it comes down, you know, and then it comes back, and then here on the other side, it's kind of breaking down on me, but here on the other side, so here's a coil side A and here's a coil side B, and, you know, this is the length, this would be the length of the conductor that would be subjected to the magnetic field, and here's the other side of that coil that would be connected to the or exposed to the magnetic field. You know, this area is just connection, you know, that would be you know, in the construction of this armature. And then this, what I'm trying to show you here is, you know, this would be out the other side where we're connecting to the commutator segments. But what we're talking about, you know, this would be a coil. Now, this would show like a coil with just one turn. But actual coils, and let me do some erasing here and clean this up a little bit. Actual coils are not that way, because what we want is more more coil in a particular space. So normally what happens with a coil is you would have, I'm just showing one side here, okay, and then that's all connected together to here, comes out the other side. Then you'd have, you know, something similar here. So each strand or each particular part of this coil, you know, that's called a turn. So instead of having, you know, just one turn, you have multiple turns. And that's important when we go to calculate what the Z number is, when we're trying to figure out what the Z number is. Because Z is the total number of conductors. So if I'm looking at this, you know, the total number of conductors, say it had 4 turns here. If it had 4 turns, that's 1, 2, 3, 4 conductors. And over here, there are 4 more conductors over there. So, you know, that's where that comes from. In calculating the Z number is the hardest part of this. So if I'm looking at this example, and I'm using equation 4.1, the Z number would be equal to, in this particular problem, and you got to know the background to be able to understand this, because he tells us up front that there are 90 slots. Okay, if there are 90 slots, that means there are 90 coils. So there would be 90 coils that look like this. And also the other thing, it's not asking for it in this, but we would know that there would be 90 commutator slots. So slots, coils, and commutator bars are always going to be the same across there. So if I want to describe the total number of conductors in this, okay, I'm going to just look at this one coil. So instead of counting all of those, I'm told it has 4 turns. So I've got 4 turns. I've got 4 turns 2 times. I've got 1 here and 1 here. So I'm going to say times 2. And then how many of these do I have? Well, I've got 90 of them. And I knew that because I understand earlier from the description of the DC generator that 90 slots equals 90 coils. Okay, so I write that down here. And then it's just a matter of going through and doing a simple multiplication across there. So I've got 4 times 2, which is 8, and 8 times 90. 8 times 90 is going to be 720 conductors, and that's the Z number. And that's the hardest thing in any of these problems. Now, once I know the Z number, it's easy for me to calculate the voltage that's generated, because I plug in for Z. Well, let me write the whole thing again. Okay, so the Z is 720. The speed of this is 600 RPMs. It's pretty fast. And the flux density per pole, that would always be given to us, you know, because that measure is not something that we're normally, it's not easily done, right? So normally that's going to be given to us. And we divide everything by 60. All right. So we go through, we punch this into our calculator, we multiply it out, and what we come out with is the generated voltage between the brushes would be 288 volts. That's at no load, and that assumes that the brushes are at neutral. Okay. A lot of stuff there. We, and then again, think about that, basic equation here and how that relates to this, right? Each part of this is incorporated into this equation 4.1, and that's how we can quantify what the voltage is. We could also utilize that in the design of a machine or the application of a machine. Okay, so that's section 4.7. Just focus on that problem, make sure you understand the Z number, and you'll be good with this.